Can be heard?
Yes, sir.
Thank you. Good evening. So we will be looking at fitting and alignment today. Last time we looked at how to use a least squares line fitting. It is like regression and total least squares. The total least squares is important even when the line rotates, even when the line is vertical. That should work. So, but we did not handle noise in that case. So here you can see in this animation, so there is a certain number of red points as you can see, and a line has been fitted. You can see it is correct. But whenever there is an outlier, as you can see, this is an outlier. You can obviously see this one is outside the general pattern of the point. Then the total estimated line gets changed. So the techniques that we studied are not robust to outliers. So paired error heavily penalizes outliers. Outliers means the error is large. So we square the error. You can see when you square a large number, uh, the resulting number is even larger. So that's why we say that the square error heavily penalizes outliers, and therefore the whole line detection becomes wrong. So therefore, what we can do is we do not heavily penalize those large errors. Now you can see we can do that by a special function. So now think about the horizontal axis here as the error. Horizontal axis here is the error. What are we talking about as error? So we want to fit a line and we are given these kind of points, right? These points are there. These are the actual points. Then these distances to the estimated line, these are the errors that we make, these dotted lines. Yeah. And we call them E1, E2, and so on, right? We can square them and sum them. That's the total error. Because we are squaring the errors, you can see if my x is the error, this axis is x. If that is the error, this error grows as square of the error. This function grows as square of the error because you have used squared error and we minimize that. So therefore, rather than letting it go for large error values, we can actually taper it out. So even if you make an error of 2, the penalty is this much. Even if you make an error of 4, the penalty is that much. Even an error of 6, penalty is that much. So this can be done by a function like that. You just do not square it, but you divide by sigma squared plus u squared. So with this function, if you plot it, you will see that you will get a pattern like that. If sigma is equal to 10, it's like that. If sigma is equal to 1, it's like that, and so on. So you can see this is called a robustifying function. By applying a robustifying function to the error, we can get rid of this problem of outliers up to a certain extent. But then there are still problems. Sigma has to be selected. It's a nonlinear optimization that we have to do now. It must be solved iteratively. Least square solution can be used for initialization, though scale of robustifying function, that means the sigma must be carefully chosen. These are the problems in this robustifying function. So choosing the scale just right is important. For example, error is almost the same for every point. The fitting is poor if sigma is too small. If sigma is too large, behaves much the same as the least squares, but if the sigma is up to some certain number, performance is okay, just right. So you can see this just right sigma you have to find. So this is a problem in this using robustifying function. They are okay, but not very good. So therefore, we want to study this thing called ransack. It's a very powerful algorithm, ransack. So let's do a brief exercise before we understand ransack. Okay. So consider the problem of estimating the um, height of the people in the class. Height of the people in the class. Okay. Mm, Average height. Okay. Average height of the people in the class. So what I do is I take one person. Okay. That means I sample one person. I ask him, what is your height? He will say I am 160 centimeters. I'm 160 centimeters. Okay. Then what I say is, okay, the class has many people. I will ask hands of people whose height is within plus or minus 2 of this height. Yeah, plus or minus 2 of this height. So if about 10 people agree, let's say, I select those 10 people and I average the height. Okay. Because 10 people agreed that their height is 160, maybe 161, maybe 159, like that. About 10 people agreed with this sample that I took. So you can see, I randomly sample a person, yeah, and I get the consensus. How many people agree? That this one is called the consensus. If that consensus is large, I can take the consensus, I can take that as a correct sample, take the consensus and get the average. I think that your class had a person of height maybe 180 centimeters. So he will not agree with this 160. So therefore you can see this outlier is not taken into this averaging. So you can see at once this Randstad is able to filter out outliers. I hope that is clear to you. But what I took here is a problem where only one variable has to be estimated, the height, in computing the average height. But there are many problems with different number of parameters that we have to estimate. For example, if you take a line, you have to estimate to compute the line, like for example, y equals mx plus c. If you take this parameterization, mx plus c, two parameters have to be estimated. So we need 2 points to estimate the two parameters. So I had to make two samples at a time. So here I had to make just one sample. Here I had to make two samples. If you take the thing about fitting a circle to a certain number of points, you know that the circle can be drawn with 3 points, right? So I need 3 points to be sampled. Yeah, like that. For different kinds of fitting that we do, we need the different number of points in the sample, different number of data points in the sample. So we will now properly study Ransack. It's a beautiful algorithm. Okay, now let me pictorially show you what happens in the robust line fitting using random. So now you can see point distribution here. You can clearly see there is a line. This is the line. Actually, you can clearly see because you are human beings. You can clearly estimate this line, and you know that these are outliers and these are outliers. So I better sample 2 points like this, right? If I sample 2 points like this, I will get the line correct. But if I sample 2 points like that, I will not get the line correctly. So this is the kind of thing that we have to do. So with this animation, I will show you how this happens. Okay, so please watch now. All right. So basic ideas, let each point vote for all the models that are compatible with it. Hopefully the outliers will not vote consistently for any single model, that the model that receives the most votes is the best fit to the image. Okay. So the procedure is randomly choose a small initial subset of points. In this case, because we have to fit a line 2 points, fit a model that is to that subset, fit a line, find the inliers, so the consensus of the close points to that line to the model and reject the rest as outliers. Do this many times and choose a model with the most number of outliers, most number of inliers, outliers. Okay, let's see the animation. So this is the least squares fit. You can obviously see the least squares fit is not good. Oh, here, assume that you sample these 2 points. Can you see the 2 points that have been sampled? They are obviously incorrect. They do not conform to the line. By a mistake, those have been sampled. So now you draw a line, yeah, and then you see how many points confirm to this line. Okay, so you have to find the distances to all the points, perpendicular distance. Yeah, that's the error function, and you threshold. Okay, I will say, okay, within certain distance to that line, I take them as the consensus. Yeah, say the points are consistent with the model. Not many points are there, so we discard that sampling. Take another sample. Not good again. The consensus is not sufficient. Another sampling, consensus is not sufficient. Now I got fortunately got an uncontaminated sample. An uncontaminated sample. Now the consensus is very high. So I'm very happy. So I can do more samplings, but that previous one was correct, is correct, and then I can take that as a correct and get the green dots, and using them I find the line using the previous algorithms, one of the previous algorithms that we studied. I hope the ransack procedure is clear to you. Okay, so repeat n times. You have to repeat this n times. Draw S points uniformly at random. So those S points um, are different for different models. So in this case, for a line, S is equal to 2. Fit the model to these S points. Find inliers to the model among the remaining points whose distance to the residual with respect to the model is less than t. So we have to define some threshold. So if we pick this as a line, we have to define some threshold between these two lines. We consider that as a consensus. I mean, they must be of equal distance, like that. So the consensus. If there are d or more outliers, accept the model and refit using all the inliers. This is the procedure of ransack. It's very, very powerful. So initial number of points, typically the minimum number needed for fit a model. Distance threshold for t for inliers is required. These are the parameters. Need a suitable assumption. Example, given 0 mean Gaussian noise with the standard deviation sigma, t, the threshold can be 1.96 sigma, which gives 95% of probability of capturing all the inliers. So the threshold is sort of defined by the standard deviation of the point. Consensus set size, d, should match expected inlier ratio. Number of samples that you have to do, so that we have to compute. Choose n so that the probability p at least one random sample is free from outliers. Example, p is equal to 99. So we have to compute assuming in outlier ratio of e. This is the answer that you get for capital N. So I will slowly walk you through how this formula comes. So please pay attention to understand how this formula comes. Okay. So first of all, let's think that the outlier ratio is 40%. What that means is 40% of the points are outliers. That means that this is line like that, these dots. So these you can see these are all inliers. Yeah, because they conform to the line. But then if you have points at these locations, these are we know as outliers. These are outliers. So we can consider only 40% are outliers. In this case, it can be larger. Okay. Do you agree that the inlier ratio is 1 minus E? If 40% outliers, 60% are inliers. Very simple, right? Then we have to pick S points, example 2, for a line. Probability of all the points being inliers is, so the first point has to be an inlier, that means probability 1 minus E. Second point has to be an inlier, that means 1 minus E. So 1 minus E times 1 minus E is what you get here as 1 minus E to the power of S. Okay. Then probability of the sample of S points being contaminated is, contaminated means both are good. So we have to get 1 minus both are inliers probability. So this is the probability of sample S points being contaminated. So this sample is contaminated, it's bad. So probability of all N samples being contaminated. So let's say we do this sampling 10 times. All the 10 samples are contaminated. So that one, we have to take this number and raise it to the power of n to consider that, right? So then we can say at least one sample being free of contamination means you have to get the opposite of that. That means 1 minus this probability. So now you can see that should be at least 1 minus p. Yeah, yeah. That should be that should be p. This should be p. That should be p. At least one sample being uncontaminated should be p. This is p. So you can see now when you take p to the other side, you get this formula. So then by taking the logarithm, you can get this. So therefore, if you know the inlier ratio, outlier ratio, that is E, and if you know with what probability you want the sampling to have at least one outlier free sample, you can compute capital N, how many times that you have to do sampling. So when you consider this formula for different models, for example, 2 points means a line. And for different outlier ratios, maybe 40%, you can see the minimum, so the total number of samplings that you have to usually do to get at 99% uncontaminated sample. So 11. If you have a circle or something, for 40%, 90. If you have, this is a homography, you can estimate a homography using 4. There are other models also with that number, maybe 34. 7 fundamental matrix. If you want 30, if you have 30% outliers, you may have to do 54 samples and so on. So this is the idea of this. So you can see with the outlier ratio, it quickly grows. This is the outlier ratio. Yeah. Okay. So Ransack works. So you can code Ransack if you like, but it is a little bit cumbersome to code it. Good things are simple and general, applicable to many different problems, often works well in practice. Bad things, lots of parameters to tune, and doesn't work well for low inline ratios, too many iterations, cannot always get a good initialization of the model based on minimum number of samples. This is the thing about Ransack. Okay, so we covered Ransack. Thing about Ransack is is a very powerful thing, but after that, method called MLESAC has been introduced. So therefore, if you know about MLESAC, you don't have to use Ransack. You must use MLESAC. Yeah. Then let's look at the Huff transforms. Huff transforms are also good to estimate lines and so on. This is a very powerful method. It's a voting method. Huff transform is also a voting method. So you can see many lines are there in this. So they have fitted a line using Huff transforms to this. Yeah. So let's see how that works. Yeah. This is possibly an earliest voting scheme, but still it is very useful. Describe the parameter space, discretize the parameter space into bins. For each feature point in the image, put a vote in every bin in the parameter space that could have generated that point. Find bins that have the most votes. Okay. Okay, now you have to carefully understand this, how that this works. So consider that this is an image and consider this is a Huff parameter space. So you can see these points, they sort of conform to a line. Okay. So that Huff parameter space, now let's say that we want to fit a line and then this space is in M and B. Can you see that? It's a different parameterization. So we have to find this M and we have to find this B. What we have is a set of points that may or may not correspond to a line. Okay. So what does a line in this image space correspond to? A point in the parameter space, a particular M and particular B. That it corresponds to. So take this x0, y0, for example. Now assume that this is a point in the image space. Now that should correspond to this line in the Huff space, because now x0 and y0 are fixed. B and M are the variables. So therefore, this is like also a line. So you can see the line has been drawn. I hope that is clear to you. All right, take another point. You take that point, that will also correspond to some another line. You can see this x1 and y1, that may correspond to another line. These two are fixed, and M and B are the variables. Okay. So like that, when you get many points, you start drawing these corresponding MB lines, then finally you'll realize that there is one bin that has the highest density. That is the bin that corresponds to the correct line. So with that bin, you can estimate, you can get the correct B value and the correct M value. What a beautiful technique. I hope you understand that. Yeah. If you have any questions, as before, you can interrupt me and ask at any time. Turning on the mic, or you can type a message. So yeah, if there's anything unclear, please tell me. Okay, so you can
Sir,
see.
is
Yes.
the first one more like regression and this one more like clustering?
It's a good question. Actually, we do not, in this case, we are not doing regression. We are not doing regression, but we want to do the parameter estimation using this voting scheme. Okay, so this voting scheme happens like this. Now for each of these points, now let's take this point. Okay.
So, but the reason I asked the question is in the picture of the parrot, there are a number of locations where it's like marked, highlighted. So I was wondering why if that because of that reason, whether it's like a kind of clustering, like where it's highlighted
In the
certain
parrot image,
areas.
yeah, that's a very good question. In the parrot image, many have very high intensities, right? The reason is there are many lines. Corresponding to these lines, these intensities are there. So this is the half parameter space. There, if the intensity is high, that corresponds to a line. Reason for that is this one. If you take any now set of points, okay, we do not know whether there's a line. You take any point like this, so that point, let's say, is x2y2 or something, x2y2 or something, okay. Then the line that correspond line, if the line we assume is y equals mx plus b, this point should conform to that line if the line is given. Okay, we don't know it. So that means I must be able to write y2 equals mx2 plus b. If you put that into the line, it must conform to the line. Yeah. But here we don't know m and b, so these are the m and b are the parameters. So finally we can get minus b equals mx2 minus y2. So now you can see this is like another line, but this is a coefficient, this is a coefficient, m is not known, b is not known. With that, we draw a line here. For the next point also, we draw another line. For this point also, we draw another line. For this point also, we draw another line. These so many lines after we draw, they will cross at one single point. That single point corresponds to one b here, this b, let's say it's 5, and one m, let's say it's 2. So now we found the parameters of the line. M is 2, b and 5, b is 5. So you can see each point votes in the half parameter space. This is the idea of half line. That's what you saw there. Like so. Yeah. I hope that is clear. So now the parameter space representation, the previous one had a problem. In practice, we won't use M and B space because it is unbounded. M is unbounded, B is unbounded. So vertical lines require infinite M. That's a problem. So therefore, we have another parameterization using the polar representation. You can see in this case, we can take the perpendicular distance to the line and the angle theta. So then a line can be written as rho equals x cos theta y sin theta. Yeah. So I hope that it's okay for you, x cos theta and y sin theta. So this is a parameterization line. So the two parameters are, one is theta and one is rho. These are the two parameters. This is what we use in the half parameter space. You can see this rho is not very large because then the line has to be so far away from 0, and theta is between 0 and 180. That's all we need. So you can see this is the rho theta parameterization. So we have divided that half parameter space into bins, and we call it an accumulator. It accumulates things. For 0 to 180, for each feature point, we have this, and we plus 1 to a bin. So we add 1 to that bin, add another 1 to that bin, like that. If any line, any point corresponds to that. So this is the thing we do. Find values of theta rho, where theta rho is a local maximum. Perform non-maximal suppression on the accumulator array. The detected line in the image is given by then rho equals x cos theta y sin theta. if we find particular theta and particular rho by maximizing this. That's how you do this half. So you can see, for example, for this kind of a set of points, see you have peak there. So in the half space, this is the rho theta space. So from that we can estimate the rho value and the theta value. From that we can plot the line. This is the idea of that. So for a square you will get 4 points because there are 4 lines. Then for a circle you get something like this, and so for several lines you get some crazy things like this. Yeah, for the parrot line, because there are so many lines, you get that. When there is noise, this line crossing point becomes fuzzy. There are many things, so peak gets fuzzy and hard to locate sometimes. So when you have too much noise, you cannot do that. So dealing with noise, how to choose a good discretization? Two course large votes obtained when too many different lines correspond to a single bucket. To find, that means very small binds, miss lines because some points that are not exactly collinear cast votes into different buckets. Incremental neighboring means smoothing in accumulator array, those kind of things are solutions. Try to get rid of irrelevant features, take only edge points with significant gradient magnitude and so on. So transforms, good things, can deal with non-locality and occlusion, can detect multiple instances of a model, some robustness to noise, noise points unlikely to contribute consistently to the energy bin. So this you can see that also can get rid of outliers. Leads to surprisingly general strategy for object localization. More on this next. Horn's complexity increases exponentially with the number of model parameters. So for the line, it's okay, but when your line has 2 parameters, when you have 3 parameters, 4, and so on, you can see the bins become extremely large. For a 3-dimensional space, now if a 2-dimensional space, you have 10 by 10 bin, that's 100 bin. In 3D, you have 10 by 10 by 10, that is 1000 bins. Like that, you can see the number of bins seriously grow in multiple dimensions. So this is the problem with the half transforms. Non-target shapes can also produce spurious peaks in the parameter space. It is hard to pick a good grid size. Those are the problems in half transforms. So let's do a brief exercise with the half transforms before we proceed. Um, so we'll do this half transforms exercise today. Um,
So is there a bin size that we have to specify? Is automatically
we have to
calculated?
specify. We have to specify. Let's see what happens. So let's create it. Yes. So first of all, let's do half line. Hmm. Let me open an image. First of all, I have to see what's that image and read the half lines. I want to use this Sudoku image. So I will send that image over the chat. I put that image in the Zoom chat, so you can use that image, Sudoku image. Um, okay. That image is called Sudoku. Sudoku. ENG. We need that in grayscale. We don't need floating point. In, and we'll check whether in has been read by running this. P is not none. No, I did not properly write PNG, right? PNG. Okay. Um, mm,
So I think that cv.im read, maybe you have to put it in yeah, commas, inverted commas.
yeah, it is. This is correct. Yeah, I'm thinking how to write the half lines. So
Ah, okay.
first of all, you have to get the edges. Okay, edges, edges. Uh, or you have to do the canny edge detection for edges. Okay, let's plot that also and see um, whether the edges have been detected. Yeah, so edges have been detected, canny edges have been detected. So for this, we want to fit the line. So edge detection is fine now. I'll get rid of this for the time being. Edges. Okay, now I can do the half lines. Then we have to plot it. Lines equals CV half lines. Okay, you can see now the question asked is very important. So we feed it the edges image, and then here we have to give the two resolutions. Where is the half function? Let me open the parenthesis again. This AI prompting is very tempting, and I hit the tab key. Anyways, so I'll tell what it is. You can see the edges. This is the edges image that we have given. So we can see the resolution, uh, the pi divided by 180. Pi divided by 180 is the angular resolution. Uh, 1 degree. This one is something threshold, I think. So this is okay. If you want, you can look at the half lines help in OpenCV or OpenCV doc, right? OpenCV doc. So you can type half lines. This is 4.13 half line. So you can see uh, in Python, image, row, theta, threshold. Row means distant resolution in the accumulating pixels, 1 pixel. Angle resolution accumulating radians. So you can see, as you rightly asked, it's a very good question. You have to give that. Okay, now I have the lines. I have to plot these lines. This is the annoying thing. So for line in lines. So now I'm going to write a for loop and plot them. Oh, see, now it's giving all the way to, I have to extract rho and theta, rho, comma, theta, rho and theta. I have to extract as line 0. This is, you have to tempted to hit tab. Line. Okay. Then I have to get the, how to plot the line, get the number. So A is, as you know, np dot cos theta. We can take that as that theta, and B is np dot sine theta. That's okay. Then we can see x naught. X naught is A times rho. Y naught is B times rho. This is the 9 parameterization. Then you have to compute two points in that, x1, y1, x2, y2, and then you can draw a CV line. CV line on IMBA. I think we have to make a copy of that image. So let's make a copy of that image. In with line, we will copy. In that, we will plot the line. Okay. Then we can display that. I'm plotting half lines. Yeah. Input image and the half lines. I want to plot the canny edges also. 1, 3, 1, 1, 3, 3. And I plot the canny edges here. Here is plot edges. Canny edges. Okay, I hope this is correct. Let's run that. Only CV2, no attribute CV2, line CV half CV. I put CV2, that's a problem. So I can use NP import numpy as NP. What does it say now? Inline CV copy, CV2 has no attribute, copy. Okay, I don't remember, so I will search on the internet. You can use
So can you directly use im.copy?
im.copy, right? Yeah. Thank you. Yeah. Okay. Okay. Thank you very much for that. Yes. Half lines. So good. I think I had to convert that to an RGB image. Yeah. So convert that to an RGB image. Then I can draw the lines. Line, yeah, in some color, right? Yeah, now you can see the lines have been drawn. I hope you can appreciate that. So I will give you some time to do it. Please do it, then you will feel very happy. And you can ask any question about what we have done here. Why is it complaining? Read unknown word. Okay, so once again, you can see the half circles. So we want to detect circles in this coin image. 1, 2, 3, 4, 5, that many coins are there. And the things that we have to do are you open that coins image once again, and then you make a copy of that image. Of course, you test whether the image has been properly opened, and then you convert the copy to color because you want to plot that in color. And then first of all, we have to median blur the original image. Then in the original image, you run the half circles. These parameters I took from the previous example that I did at home. So that you have to read about from the OpenCV help on half circles, unfortunately. So that help is here. You can see, you can get the half circles help and read about what these things mean. Yes. So I'm sorry, I don't know what to say about those things. And then once the circles are there, I convert to in16 for each circle. So this is how you get each circle called I, and then I0 and I1 will have the center, and I2 will have the radius. That I get from documentation. I draw something at the center, that is this dot, and then I draw circle at that radius, at that center with that radius, then these kind of things are drawn. You can see it's a beautiful thing, right?
So why is there a dot at the middle of the coin on each of them?
Oh yeah, I drew a dot at the middle. You can see the first circle that I plot is has radius of 5 or something, right? That's just a dot. I'm drawing two circles at each point, as you can see. So the first circle that I'm drawing, this one,
Okay.
you can see it is just a radius 1 circle with thickness 5. So it's that dot that I'm doing. And then this one. So you can see
Okay,
the
see,
color
great.
is also different. So let me choose a very different color. Then you will see the difference. So I use a different color there. Thank you very much for those questions. Now we have now you can see the use of those. Like if you have a conveyor belt and these coin-like things are coming, to quickly detect them, you can use half circles. But one thing is you have to median filter it. Otherwise, these kind of problems can happen. So initially, when I did not median filter it, you saw that so many circles were detected, right? So that kind of little bit of filtering is important. We studied about median filtering some time ago. All right, so we can go back to the slides again. That's about half circles.
So if the circles are these coins are on top of each other, will the
Then nothing much can be done with half circles.
okay.
Yeah. So these are very simple methods now, so they are not robust to those kind of things. You're asking the question, what happens when there are occlusions? When something is covering something.
Exactly.
These things cannot handle occlusions.
Okay, sir.
It will draw something, but it's not very, I mean, it will draw a circle, but at least one will be missing. So you can test it out
Okay, sir.
with a different image. Yeah, that's a good question. So these kind of things are there with half transforms. So then there's a thing called generalized half transform also that can detect any shape. So we got lines and we got circles. It can do any one or any shape also. Generalized half transform. But I will not go into too much details about this. But I will show you only an image of that. Maybe how that has resulted in. So there's a you can go through the slides and see what it does. So you can based on this you can detect things like um, they have not given a model of the inverse after. So yeah, yeah. You can detect shapes like cars and so on with generalized subtransform. It's showing what it does. It will take different shapes of the car and vote for a place. So using that, you can do that. Okay. So this is what we want to do about the fitting exam, fitting as lesson. Now let's look at the alignment. So you can see now slowly we are doing little slightly high level operations. Now we want to do alignment. This is a very important lesson because different ways of transforming images is important in industrial applications. But in the image alignment slide here, they have shown me some beautiful examples. This is called look into the past. You can see they had a very old image of this same scene, and they have placed that in the new picture. In the new picture, they have put the old image. Beautiful, right? Like some time ago, like maybe 50 years ago picture, they put it here. It's called a look into the past. So these kind of things can be done. And sometimes you have seen on the cricket ground, they display an advertisement that looks like popped up, right? Those are also done like that. So let's look at some images of that. Artificial advertisements of cricket ground. So some of these advertisements, yeah, something like that. So this advertisement you have artificially put. It's not actually there, but when you see it, you see it as a popped up thing. Yeah, this is a real one. Okay, these are artificial ones. Yeah. That can be done. Then different things. So one application, one of the students did is actually he was an excellent student. I will describe these kind of lessons, these kind of theories. What he did was this. He was a tennis player, anyways. So he did. Now, when you have the tennis court is there. Tennis court is there, so you know the net is something like that in the tennis court. That's the net. So the actual size of the net is very well known. Actual size of the court is very well known. So using this, the actual size of the net, he was able to do the ball replacement in 3D. He was able to do 3D ball tracking with that. Maybe in cricket you have seen the Hawkeye, right? Let's see the Hawkeye, if we can find a quick video, Hawkeye video. Yeah, I think it's called Hawkeye. Yeah.
Park Avenue, long-lasting fragrance, unshakable confidence.
I might have found one of the most influential moments in professional sport. Something that has changed football World Cups, Grand Slam tennis, and potentially the World Series of baseball. The event happened on the 5th of June, 1996, in a minor counties championship game that I am assuming had less than 100 people in. Cool. Of course, some of that does make sense because the hawker can see exactly where the ball landed, rather than what we do in cricket, which uses the science to estimate where it will end up. But there is no doubt of the impact that technology has had from the start. As I said earlier, cricket has just changed because of what Hawkeye has taught us. Leg before wicket decisions are nothing like they were in the late 90s. In those days, fast bowlers could get so many LBWs that were quite clearly going way too high. Spinners couldn't get LBWs at all if the batter was even slightly out of their crease. Now the tweakers get rewarded for hitting stumps, and the seamers have to come up with other methods. Now, when an international player...
So you can see the applications of this. Of course, you have to do many more things to get this kind of thing working, but generally the principle you can understand by going through this lesson. Yeah, let's go through this. I hope you are interested in this. Okay, so now we know that we can fit a transformation by taking the residual and minimizing that. That's what we have been doing, right? So even when we did the line fitting, you remember we found the residual. That means the distance between the line that we think is correct and this distance. We took that, we squared it, summed up, and then we found the model parameters by doing that. So then when you find the model parameters, we can draw a line or something. But this is applicable not only to a line, but to many other models that we want to estimate. So in this case, one model can be the so-called homography. That means if you have two planes, how the points move. For example, we know that this red point matches with this red point, this yellow point matches with the yellow point, and so on. We know this pink matches with the pink, this blue matches with the blue. We know, but they have moved. That motion you can compute as a transformation. So these are the things that we want to do in this lesson. So finding out of transformations, affine transformations, homographies we'll find, and robust alignment also we'll briefly look at, and large scale alignment we will briefly look at that. Okay. So one application is this so-called panorama stitching. I think in the phones also some form of this panorama stitching is there, not very extravagant. So you have two images of the same scene. The parts of the mountain are in both the scenes. That means some part of the scene is in both the scenes. So therefore, what you do is you do this so-called alignment, and then you can overlap one image with the other. So like so, and then you can have a larger spans of the scene in that one image. So auto stitch and all sorts of things are there. In fonts also these things are there, and so on. And then contemporary and historic images and look into the past. I showed you at the very beginning something like that. This is also an application. Then using these techniques, you can find objects in images. That is also possible. These are from David Lowe's image, finding these things in the image. Yes, and then those days, when you wanted to find something on the internet, find similar images, these kind of techniques could have been used in those things. So these are called visual landmark recognition, will be told. And then finally, large-scale reconstruction is done by advancing these techniques, but that will not be discussed today. But later on, these kind of things can be discussed, how to make a large reconstruction. Yeah, okay. Let's see how this is done. First of all, we find a set of feature matches that agree in terms of local appearance and geometric transformation. Those feature matches, we have learned them as SIFT. SIFT, and I had told you there are SIFT, and I spoke about Colmap, and I spoke about superglue. These are so-called features, and they can be found in both the images. So their local appearance vice versa same, and you can use geometric configuration also. They agree. So and then we do the panorama stitching by matching. So I have shown you this image before. So this row is looking at that, and this is the place where the row is. So you can see on the Mars. So you can see, yes, even as a human being, you cannot co-locate these places. Yeah. So we looked at this image also. The same feature, these assist features can be detected irrespective of the viewpoint transformations and the lighting changes. Yeah. So finding transformations, find and homographies. Let's see how to do this minimization and find those transformations. So first of all, we have to see what these transformations are. So let me briefly take you through these transformations before going into this. Okay. Now these are basics of computer graphics. Actually, not computer vision. Actually, assume that you have a rectangle, a square. The square is here.
So can I just jump in and ask a question?
Absolutely.
Now we are discussing pictures here. Now you brought the example of a video. So does that mean the same principles apply for pictures and videos?
Video of the Hawkeye, you mean?
Yes, like that match that movement of the ball and. So you can answer it later if you want to take it.
You are asking me how Hawkeye is done.
No,
Yes,
not necessarily, but you gave the example of
yes,
the
yes,
principle, and then
no,
it's a
yeah, I will describe that. It's very important to describe that. So now assume that the cricket pitch is like this. This is the cricket pitch. So the bowler stands here, comes up running and stands here, and he will deliver the ball. The ball will take this kind of path. Take this kind of path. Ladies in the class, the ball has to hit the pitch and then come to the batter. I'm sorry, some of these ladies do not know how a ball is bowled in cricket. So this is the path of the ball, right? So you can see at different times. This is okay. Let's call it that t equals 0 milliseconds. T equals, I don't know, 10 milliseconds. T equals 20 milliseconds. T equals 30 milliseconds and so on. Okay. So ball travels like that. So you have to have cameras, several cameras. I don't know the camera configuration that they use. I haven't studied that. Let's assume that you have a couple of cameras looking this way, that way, and that way. And that way you have several cameras. So in each of these camera images, in this one, we will take t equals each time slot we will take. So for example, we will take t equals some t number t1. In this one also we will take t equals t1. In this also t equals t1. In all the cameras we take the t equals. That means each camera has to have the synchronized time. That's why it must be an expensive system. And each of these cameras, you will find the ball in some place. This is the same time, but you will find the ball in some place. So you can see in multiple views, the ball is now located. And there is a technique called 3D reconstruction. So you can simply think about that as triangulation. We will discuss that. Using these multiple images, you can estimate. Now let's assume that this is t equals t1 that time. You can estimate the 3D location of the ball. That means you can estimate with respect to some coordinate system in the ground. You can estimate its x coordinate, y coordinate, and z coordinate, right? And of course, you know the time. The time is at t1, right? Okay. So what that means is, after doing this process, you have x1, y1, z1, t1. That is for the frame number 1. Frame number 1 is a set of images. Then at frame number 2, x2, y2, z2, t2, and so on. Now, if you have all these x coordinate, y coordinate, z coordinate, and the time, then you can generate an animation with the cricket pitch in the view, right? That's what Hawkeye is. So you know how ball travels 3D with respect to the coordinate system of the ground. So with respect to the coordinate system of the ground, we know exactly where the wickets are, the height of the wicket, and then we can exactly tell whether the ball hits the wicket or not. And we can do a prediction also, right? You know, projectiles. You can do a prediction if you have several points in the projectile in 3D. projectile in 3D because we have to consider the swing also, right? Swing, wind speed, all these things we have to consider. I think you can fit a curve in 3D to this. Not only the projectiles that you have done in A levels, I think you have to fit a curve in 3D and get this. I'm sure that these people who developed this must have studied this much more harder than this little thing that I can tell about this. But it's a very interesting question and a very interesting application, as you can see. Actually, directly, it's a beautiful thing.
Thank you, sir. I was just
So,
thinking maybe we can put a GPS or something inside the ball, and then maybe we can track it.
do you think that DPS will survive with the impact when the player hits? Oh my goodness.
Just an
I don't
idea,
think
sir.
so. I don't think so. Oh my goodness. How hard does it hit, right? I mean, if it hits on your face, you sort of die, right? If you don't wear a helmet. So this is not possible. But even then, do you think that GPS can track this fast? Not possible. These are high-speed cameras, okay? These are not even regular cameras. Regular cameras work at 30 frames a second. This is not enough to track the ball. These are high-speed cameras, synchronized high-speed cameras. Yeah,
Thank you, sir.
yeah. This is the GPS thing that doesn't work actually. Doesn't work due to both the reasons. Yeah. So I hope I answered the question and you are sort of happy about this. I'm glad that you asked about some industry application, and I was able to say that this course is industrial automation, right? So mission-based automation, and I just should not talk about theory. Okay, theory can be applied, but it is not easy as a theory and simple example, right? Okay, let's take a square in the coordinate system like this. Square. This is a square. And let's draw the cone of the square like that. This is that cone of the square. So now I'm going to transform this square. I can rotate it and translate it. So if I rotate it and translate it like so, exactly the same size, and its the center is maybe somewhere here. So in this case, I'm assuming that the lengths remain the same. This length is equal to this length, this is equal to this, and so on. They are the same. They have not changed. The angles have not changed. They are still 90 degrees. So this kind of transformation, we call it Euclidean, Euclidean transformation. Euclidean transformation. But this is only one of the transformations that can happen. In robotics, you will study directly Euclidean transformation in 3D. This is actually in 2D. But what are the other things that can happen due to different kinds of things that you can do on these geometric shapes? For example, you can affect the transformation like that. You are not only rotating and translating, but you are scaling also. Still, it's a square. Still, it's a square, a rectangle, square, and the sizes are different but equal. Different but equal. And rotation and translation, this kind of a thing, when the size changes isotropically in all directions, we call it a similarity. Similarity. But this is not only that, due to other things, due to actions of cameras and so on, different things can happen. Sometimes this can become a rhombus. This is a rhombus, not a parallelogram, I'm drawing rhombus. So therefore the sides are still equal. But the angle is no longer 90, you can see. This kind of transformation we call an affine transformation. Affine transformation. But the action of a camera is even more complicated than that. Due to action of a camera, this square can become a quadrangle, just a quadrangle like that. Angles are gone, line parallelism is gone. Okay, even here the lines are parallel to each other, but were parallel are still parallel in this. In both the previous cases also, the lines that were parallel are still parallel. This kind of a thing is called a homography. Homography. So if you take about Euclidean transformation, you just need three numbers to specify that: the translation and the rotation. Yeah, three numbers. I hope you agree. You will just need three numbers. For similarity, you need four numbers: translation, XY translation, rotation, and the scale. Yeah. For this, you need six numbers because shear is there. For this, you need nine numbers. So with different kinds of numbers, you can specify these transformations. Yeah. Okay, so I'll show you this mathematically slightly. So first of all, you have so-called isometries, and they capture these Euclidean transformations, and then this is also there a sign change, but they are forget about the sign, rotations and translations, R and T. This rotation matrix is cos theta minus sin theta plus cos theta, and this is the translation. I will do it and show you. And similarity, there is a scaling parameter S everywhere. Because of that, the size can change. Affine, you can see A11, A12, and so on. 6 parameters are there for affine. 1, 2, 3, 4, 5, 6. Affine. But remember, in the affine transformation, notice the last row is 0, 0, 1 still. Here also the last row is 0, 0, 1. Here also the last row is 0, 0, 1. To represent a 2D coordinate, we are using three numbers. That's the thing. That's how we do it. But if you take a projective transformation, it is just a transformation like this. All 9 numbers are there. Only 8 degrees of freedom. So I lied you here. Although 9 numbers are there, only 8 degrees of freedom. Yeah. Okay. So let's do a simple exercise with this and see. Oh, by the way, before going that, I will show that how this happens in reality. So you can see a similarity transformation here. You can see the tiles, they are still squares. You can see the lines are still parallel, they are squares. But in the projective case, you can see the lines are not parallel. Do you agree that the lines are not parallel? I hope you can see that. So here the lines are parallel. Yeah. Lines are parallel. Here lines are not parallel. Here you can see the shapes have changed into rhombuses. This happens due to different kinds of imaging situations. Yeah. So we want to briefly draw some of these things. Yeah, I will do a little bit of coding, and so that you can see that you can get them affected. So import matplotlib pyplot.plt numpy. That's enough for us. So we'll get the points A, B, C, D. Points A, B, C, D. These points I'm defining as A, comma B, comma C, and D as 0, comma 0, comma 0, comma 1. First point is 0, 0, 0, 1. Actually, I should define that as a vertical number. This is the first point. Oh, 0, 0, x is 0, y is 0, and there's, of course, as I told you, there's one more coordinate at the end. Remember that. Is it too complicated if I write all these things together? Yeah, it is, right? So we define A first. A is like that. Then let's define B. B is, we can say x coordinate has changed to 1. And then C, B is this is point number C. There both the x and y coordinates are 1. And then finally D, last point. Yeah, only the y coordinate is 1. Then we can mm, show that as all the points as a matrix. X equals, we can stack them, horizontally stack them and do it. So if we can paint mm, I want to plot it and show you. Okay, to plot this, I need to get small x as I need to do a cycle, right, actually. This one. NP append. I want to get in the capital X, I want to get the first index and all the columns, and I want to append x's first one again, because I had to get a cycle of this. Okay. I hope it is correct.
Can you use the AI prompting to help you?
Yeah, of course. Yeah. So now you can see 1, 2, 3, 4. 4 points are there. What I want is I want from the small x. This is the small x. So you can see the x coordinate 0, 1, 1, 0, and I have put the first 0 also again because I want to plot this. So I want this now. That's the reason. You will see when I plot it. Okay. So append. Okay, these coordinates. Okay, that's done. And then what I have to do is I can plot it. Figure Ax equals CLT dot subplot 1 comma 1 or something. Ax dot plot. I want to plot x and y with color equals green or something. MPAD dot show.
So there's a plot PLOT.
Thank you. So you can see that this is the one. I have to, you will not see anything if you do not write x aspect ratio equal. Otherwise, you will see it. So this is the square. That this is the square. You can see 0, 0, 1, 0, 0. This is 1, 0. This is 1, 1. This is 0. So then I have to draw this line also. That's why this is the appending thing. Okay. So I'll let you plot this by yourself so that you can. I can do the transformations and show you. Okay, I hope that you have gotten that right. So now I want to create that transformation. First of all, let's create a similarity Euclidean. np.array. Okay, first number. I hope you remember that the first number of this turned out to be np cos theta. So I have defined the cos theta. Theta, let's say 30 degrees. Cos theta. And the second number is minus np dot sin theta. Third number is a translation. So let me define the translation vector tx comma ty. Okay, 1, 2. We translate by 1, 2. Let's do 2, 3. 2, 3. So sin theta. And the third number is tx. Yeah, okay. Second row. Okay, it takes me to a new row. Second row is np sin theta cos theta ty. That's correct, I think. Then finally, 0, 0, 1. Remember, that's the last one you need to have. This is the transformation. Okay. So then to affect the transformation is very simple. Y equals H matrix multiplication H. That's it. That's how you do the transformation. So after that, you need to get the Y coordinates this again for the Y also. After computing this Y, I need to plot that again. I will plot that using a different color. So I'm extracting these coordinates now from not from X now. I'll extract them from Y. Why thinks it's doing this? I'm going to disable this. I think it's did doing that, right? So this must be Y. I don't know what's happening.
So are you defining the same thing two times on both the lines? Like x is equal to np append, and again at the bottom you have np is equal to. Is that part of the code?
Yeah, I'm extracting the coordinates from Y now, from the transform version. Transform version is Y.
Okay.
I'm extracting this coordinates from the y. That's why. Okay, then now I plot them again. I will plot them using red, and then you'll be able to see the transformation. So it went to a new figure. I don't need a new figure on the same figure I'm going to plot. Now you can see the translation has happened, right? So actually I need to put a little circle at the very corner. Let me let me again get it set to put a I hope it will do that for me. Oh, no.
So I think you disable the auto.
I disabled, but this I turn it on now. Yeah, this one is I snoozed. Okay, let me see. I won't only here. I think it's red. Oh, I think we have put that in the green, right? That's okay. Black. Perfect. Let's see whether it works first. Doesn't work. It is wrong. See whether that works.
I think maybe marker size underscore size. Marker underscore. Oh.
So you can see without the prompting, I cannot do this, right? Forget about it. Okay, I can get it gets corrected now that I won't do it. I won't put the marker now. Let's see whether it can correct it. Okay, fine, right? Okay, so you have put a marker there. That's fine. I won't put a marker in the next plot also. X5, and now I will not put the marker. Black is fine. Okay. So you can see now the translation has happened. I said 3 and 2. So this point has translated by 3 and 2, and the rotation has been 30 degrees because we set theta to 30 degrees. Okay. So please do that and verify that these are correct. So you can see the shape of the square is the same. Angles have not changed. Line parallelism is all the same. And only the translation and rotation has happened. Euclidean transformation. Then let's do that's okay. Let me move this part also here.
So I have a small question. At the top of the code, now each of these points, like A, B, C, D, are they 3D or are they 2D points?
Good question. They are 2D, but we are using 3 numbers to represent them.
Okay, sir.
The reason is this. That's a very good question, but I will explain that in detail later. The question is, you have only 2D points that you are using 3 numbers. It's a very good observation. So the reason is this. One reason is this. Now, if I take this point, it used to be 0, 0. 0, 0. My x-axis was like that, and my y-axis was like this. Then I wanted to translate that to 2, 3. When I translate that, I will get a point there, and that point should be 3, 2. Sorry, like 2, 2, 3. Those are the Cartesian coordinates of the points. But I want to affect this using a matrix multiplication. So in order to do that, this is the way to do that. So this is without rotation, the rotation translation matrix 0, 0, tx 0, 0, ty and 0, 0, 1. So it's a 3 by 3 matrix. It only affects translation. But now you can see, if I want to multiply this by a vector here, right multiply by vector, since I have 3 numbers here, I have 1, 2, 3 numbers here. I have to have 3 numbers there. 1, 2, 3 numbers there. And also we will notice that, okay, whatever the number here, 0, this 0 I'm writing, 0, this 0 I'm writing. To get the translations working, I have to have 1 there. I hope you can realize that. This 1 is so important. Otherwise, this multiplies with this multiplies with this, and this multiplies with this. The translation Px has to multiply with this 1. Then only I will get that added. 0 times 0, 0 times 0 plus Tx times 1. Then you can see this 2 comes here because my Tx is 2. So you can see the last coordinate is important to affect the translation. So
Okay, sir.
translation is affected using a linear operator. Linear means matrix multiplication. Linear operator. So translation is actually inherently not linear, but we can affect a non-linear thing using a linear operator because we have one more coordinate than the 2 coordinates. It's an important thing. These coordinates are called homogeneous coordinates. They have a special name also. So we will be talking about those things a little bit more also later. That's a very important question.
Yes, sir.
Yeah, so again, you can see why we had 3 points now. So the coordinate A, we had 0, 0, 1. Coordinate B, we had 0, 0, 1, 0, 0. Actually, it's 0, 0 coordinate. This is 1, 0 coordinate. This is 1, 1 coordinate. This is 0, 1 coordinate. The 4 corners of this rectangle 0, 0, 1, 0, 1, 1, 0, 1. So those have been translated like that and rotated. That one is the Euclidean transformation. Euclidean. Okay, that's Euclidean. So now let's do a similarity. For the similarity transformation, you know that the same things exist. But remember that each one of these is multiplied by scale like 2. So this multiply this by scale. This is multiplied by scale. This is multiplied by a scale. And this is multiplied by a scale. Now when you do that and plot it, we will plot it using what color should we use? What color? Red, blue. Okay. So now you can see it has enlarged. The translation is the same, so I'll change the translation so that you can see it properly. Maybe 2 and 1 and something. Translation and the rotation, so you can see, right? Rotation is 30. Let's rotate it a little bit more, 60 degrees. Yeah, you can see that now. It's a similarity. So the line parallelism is there, angles are preserved, but the scale has changed homogeneously in every axis. The translation. Then do the affine one. Let's try to see whether this AI prompting man can do that. And it's gone crazy. Stopped. Oh, it gave me. Oh, this is not correct. This is not correct. Correct. Okay. For the affine, I had to give some numbers. I will say these are not bound to this cosine 1. Maybe let me say 0.8. Here, let me say 2. And let me say 1.4, 1.5 or something. That's the affine one, h multiplied by that, and then you're drawing in yellow. So, oh, it has gone crazily squeezed, right? You can see. Make it small. You can see now it has become a rhombus, right? So translation is the same, so we change the translation and we make it 1 so that you can see. Yeah, yeah, so you can see that, right? We move it a little bit. That's your fine. 3 and 1, fine. Yes, 3 and 1 are fine. But even in the affine one, you can see the last row thing is actually still 0, 0, 1. It's very important observation. That's the affine one. Then finally, let's do homography. Projective, the same name. Projective transformation. So now here, these numbers also will change in the projective one. I wish I can get AI to prompt that. Let me see. Trying to do the same thing, right? Homographic one, I'll do it myself. Translation and so on are important. And these things are not important. Also, these things are not important. Here you put numbers in the last row. What has happened? Color is yellow, magenta or something. Is it not working? Oh, you got the same thing, right? You got exactly the same thing. I cannot understand that. Could you put large numbers here? What of it? Oh, I know why. I had to divide by the last coordinate. Yeah. Last row. I have divided by the last row. Now you can see that it changes, right? It becomes a quadrangle. Now you can see it has become a quadrangle. I think these numbers are too small. 8 and 9. It has become a quadrangle. No longer is it the lines are parallel. Are not parallel. Line parallelism is gone. I cannot show that due to some reason. What stupidity am I doing? I have to do it like this. Why for y? Yeah. So when you get y, you have to divide by the last coordinate to get the Euclidean coordinates. Last row to get the Euclidean coordinates. Now it's affected. You can see it has become just a quadrangle, right? Yeah, it has become quadrangle. So I hope you understand these things now up to a certain extent. So I'll keep this open for you to just see and do. So how the projective transformation is done. This last division is very important. Actually, for all of them, we should have done that. Otherwise, it's unfair, right? But it does not matter for the others because the last row is 0. The last row is 1. Yeah. Yes. So please, I'll keep this visible. See whether you can get one of these things working. We can get a break now, take a break now. So, welcome back. I hope you had a little break. Going to now take an image and apply one of these homographic transformations. And that's what I'm going to do. And this homographic transformation is there in along with this image. These are called the graphite images. So these are from University of Oxford, VGG group. So you can see these homography transformations have been given with those images. I have uploaded them on Moodle. You can use them. So you can see if I open that, you can see this 3 by 3 matrix is there. So they have given the 3 by 3 matrix. You can see the last number is 1. So definitely you can see it's homographic because there are these non-zero numbers in the last row. So that's the from image 1 to 2. image 1 to 2, and so on. So the image 1, image 2, image 3, image 4, image 5, and all these things have been given. So I'm going to open them and then apply a homographic transformation and show you what is the situation here. Okay, so this is I'm going to try transforming using a given homography is what I'm going to show you now. So first open these two images. So I will copy the important imports that we have to do anyway, because now you are very familiar with that. And open the two images, IM1 and IM2. Open the two images and check whether they have been opened. And then I will read the homography from their file. For this is the code. So I will go fast with this. And then let me show you after printing what that H is. So this reading has to happen. Now I have placed those files someplace here. Okay. So you can see that's the homography that we have read. So this is the homography from 1 to 2. Then this is, I'm going to write the important function now. In 1 to 2. In 1 to 2. Then the function is warp perspective. And we are transforming IM1 with the homography. And the shape has to be given. Let's try that. Then I'm going to show these with a OpenCV windows. Yeah, we can see the image 1 I show and image 2 I show, and then warped image I show. We can see this is image 1 and this is image 2. So when I show the warped image, the first image will be sort of warped into the second image. So we can see that has happened, right? So second image is rotated, as you can see, right? The first image has been rotated. How do you know this is the first image? Because we can see that this part of the image is there, this whatever that part is. In that image, it's not there in the second image. So we can clearly see what we wanted to do, we have been able to do. Yeah. Actually, this is not the exact way to warp them, but this is a simple way of showing that this is correct. So this looks like this. For example, from this line which is slanted, you can see that this is the case. Okay. So you can see it's a very simple code. So I'll give you a little time to make a screenshot or something like that. So these images I have uploaded. So if you want to transform the second image onto the first, you can get the inverse of this homography. Get the inverse of this homography. That also we can do. Second onto the first. I'll copy the whole thing. In 2 to 1 is what we are doing. So therefore, you can see in the in 2 to 1, I'm inverting the homography. NP linear algebra, invert H. And after that, apply the homography. And I have done some crazy things. So to change the second image, now you can see I have put the first image on top of that. There is some color thing. I don't know why that has happened. I think that's because I added that. Added that, not replaced. I change the color a little. I'm trying to change the color a little. Yeah, that's why I'm doing better. Yeah. You can see that. You can see that this horizontal line is continuing, right? So from that you can see the transformation has correctly happened. This line is continuing. This line is continuing. This line is continuing. This line is continuing. I hope you are happy with this. This code is better. Yeah. Then you can click 4 points and get the image transformed on the other. I will show that also now. Using mouse click points. For that, you have to do some little bit of cumbersome coding. Using mouse click points and moving. So let me not type all the code because then it will take time. And I will copy and I will only show you the important parts of the code. Okay, you can see that this import numpy cv, and we are importing. Oh, what happened? Numpy and np. N is 5 number of points that I have to click. The point 1 to keep the first image at the first point, second point, and there's a mouse callback function. And then these images, of course, you know that this location has to be accessed properly. Okay. Then the second image also, image 1 and image 4, I'm applying. But you can see I'm not importing the homography here, but I have a mouse callback function using which I can click the points. And then I'm doing the mouse callback, I'm doing the find homography function. Using the 2 point sets, I can find the homography. I'm not importing the homography this time, and then I do the work perspective as we did before. So now let's click 4 points. The code 1, 2, 3, 4. Okay, I had to click 5 points. 5. And in the second image also I had to click exactly the same points. 1, 2, very hectic. Next. 3, 4, 5. Then you can see they get stitched, but you can see it was not as accurate as the already available homography. The reason is when we click, we make mistakes and they are not accurate as the original homography. That's why these kind of little mistakes are there, but generally it's okay. Stitching has happened. So this is the mouse clicking part. So I will make this code available to you so that you can play with it. Yeah. What will you do in the class? So you click 5 points in the first image, 5 points in the second image, and estimated the homography. This homography that we estimated should generally be like the homography that we read from the file. So I hope that these things are clear to you. Any questions about that? Okay. Let's go back to the slides now. I hope that this thing that we did explained you most of these things, isometries, similarities, affine, homographies, and so on.
So what's the application of this kind of algorithms?
Yes. So one is assume that you want to display an advertisement on a billboard that's not there. So you can transform the image and put. So for example, you want to put a picture on a building artificially. Then you can do this transformation. Like that. I'll give you an exercise like that for you to do, and then you can do that and experience that it can be done. For example, on the road, you want to put an advertisement artificially. Then you can do that. Then there are many other applications like panorama stitching is one of them which I showed. Those one. For example, now assume that something like this. I'm glad that these questions are asked. Then only I remember to say these things. Otherwise, I forget to say these things. But these are very important. Now assume that this also I gave as an exercise. One of them. Assume that you have a circuit board like this, and assume that this is an image, another image of a circuit board. Circuit boards. These two circuit boards are there, but you can see in the two circuit boards, their perspectives are different. Cannot get it. Is like this and is like this. So assume that you have properly nicely soldered this board, and you want to find mistakes in the second board. Find mistakes. So we have a perfect image of the first board, and you even after the components have been assembled, you take image of the assembled board, and you want to find the differences. But rotation, translation, perspective distortion, all these things have happened in the second image. So this is for automatic visual inspection or something. There's a special name for that. In the machines, when they do circuit assembly, these kind of things happen. Then you can see whether diode has been rotated in the soldering. All these things you can detect. For that, we have to align the two images on top of each other. That's why you need to compute the homography automatically and align the image. But these things work only for plain images, for 3D kind of objects. Yeah. I hope that explains some applications. There are applications like that.
Thank you,
Okay,
sir.
so yeah, so these homographies can be broken like that. Also, that's okay. We don't have to think about that too much. So here are projective transformations. 9 numbers are there. Fine again, a similarity, a Euclidean. You can see the things that change and things that do not change also. But it is slightly more complicated than what we studied. These from the multiple geometry book. So now we have to try to see how to estimate these transformations by ourselves. In the code that I showed you, remember we used OpenCV to compute the transformation after we did the mouse clicking. So after we did the mouse clicking, we used the find homography function. But how does the find homography function work? That's what we are going to study, but we will not code it. But although you can code it by yourself from the knowledge that is there in the slides. So simple fitting procedure we use for linear least squares approximates viewpoint changes for roughly plane objects and roughly orthographic cameras, and we use to initialize fitting for more complex models if you do a affine transformation. So remember in the affine transformation, okay, let's say 5 points have been transformed like that. We can write without using the homogeneous coordinates M1, M2, M3, M4, T1, T2. So this is the rotation and this is the translation. And these are the 6 parameters that you have to estimate in the affine transformation. So we want to minimize the actual ones that you got after transformation and what you have predicted, subtracting and squaring. So this is the regular procedure that we do. Okay, so now what we do is we want to write that as a matrix form. So M1, M2, and so on, we write here. You can see the M1 gets multiplied by X1, right? So here also you can see M1 gets multiplied by X1. So X1 multiplies M1. Y1 multiplies M2 and so on, right? Then in the first equation, you have M1, M2, X1, Y1, and T1. That's fine for T1. You have 1. For others, you have nothing, 0. That answer is X1 prime, Xi prime. For yi prime also, you can write an equation. That's only for 1 point. So all the 5 points here, all the points that you have, you can write the equations like this. So this is for 1 point. How many matches do we need to solve for the transformation parameters? Remember, we have 6 unknowns, and now 1 point gives 2 equations. So therefore, you need 3-point matches for that. 3-point matches. Homography, so plane or projective transformation taking a quad to another arbitrary quad. For that, we need the 4-point matches. So this is something that we all have already done, right? So aligning these two things and panorama stitching, all these applications again. Then a little bit about the homogeneous coordinates again. So convert to homogeneous coordinates, we can put a 1 at the end, like so. And to convert from homogeneous coordinates back to Euclidean, you can divide by the last coordinate. So equation for the homography in homogeneous coordinates is like this. So this is what we have used in the examples that we did in the lines. So we can write that as lambda x prime hx. So this is my h, this is my x. There is an unknown scale here. That's what this lambda thing is. Unknown scale. Okay. So constraints from a match is like this. How can we get rid of scalar factor lambda? So for that, there's a trick. In this, you can get the cross product with xi prime. So if you get the cross product, this xi prime and that xi prime multiplies and you get 0. Remember, the cross product between parallel vectors is 0. So that's why you get this. So now you can write the cross product and so on. So you can see you get complicated equations, but I will not go through these equations. And by writing this, only thing that you have to know is now you have equations. Using it, you can find the numbers in H. Homography. That's all you need to know. So how we got these numbers, you can, if you want, you can write on a piece of paper and find them. But this is the equation that you got. Here H1 has 3 numbers. H2 has 3 numbers. H3 has 3 numbers. Are these equations linear independent? Only 2 are linear independent. So finally, you construct the system with endpoints. Endpoints like this. And then you have a system like AH equals 0. So for when you have AH equals 0, you can put all zeros for H, 9 zeros for H, and you can get 0. 9 zeros for H, you can get 0. So therefore, the so-called trivial solution is a solution for this. But that's not what we want. We want, if you have numbers, right, other than 0. So we find H minimizing this one. That's what we have to do. So there's a very well-established theory for that. Solution is given if the eigenvector of A transpose A correspond to the smallest eigenvalue. So this is how you would find, how you would solve a homogeneous system like that. So if you want to implement this, you can implement that. I don't think that it's too hard. What you do is you take the points and construct this equation. This is your capital A matrix, and you get A transpose A and do singularity decomposition. Very simple. What is the minimum number of matches needed for a solution? A has 8 degrees of freedom, 9 parameters, but scale is arbitrary. One match gives us 2 linear independent equations. So therefore, we need 4-point matches. So robust alignment. Now, although we do homographies like that, we assume that these matches are correct. But usually when you use ransack or something, SIFT matches or something, there can be incorrect matches. That's why we need ransack because these incorrect matches are outliers. Remember, in the previous line fitting one also, we used ransack to get rid of the outliers. So far we have assumed that we are given a set of correspondences between 2 images we want to align, but we do not know the correspondences. So therefore, we have to use a detector to detect them. So we extract features like that. We call these things features that we detect. These called features, and descriptors are assigned to those features as we know. Descriptors, and then we can match them. So we find the putative matches. You can clearly see that matches are generally correct, but obviously this match is incorrect. There can be other incorrect matches also. So those we have to get rid of by using ransack. Hypothesize the transformation and then see the consensus and then find the transformation. Remember, that's how we do ransack. Okay, so generating putative correspondence again. So we assign feature descriptors and we see whether these feature descriptors match. Need to compare feature descriptors or local patterns surrounding interest points. So like this, for each of these, we can have feature descriptors, shift descriptors actually. Simplest descriptor is the patches, image patches. But if we get image patches, they are prone to elimination problems and so on. Normalized correlation is also there. They all have problems, but we have to use shift descriptors. Intensity, using just intensity, it's very difficult to match them. So that's why the shift descriptor is important. Last time we saw what shift descriptor is, that it's a 120 number descriptor, and using that we can match them very well. What are the advantages of descriptor or OPXs? They are less sensitive to elimination changes. Pooling of gradients or subpatches achieves a robust small fix, but still preserves the spatial information. So we generate correspondences, but we can have problems. For example, if you take this F1, this exactly looks like this F2 prime and F2 prime, right? So there can be wrong matches. That's why we have to use ransack. Compare distance of the nearest name to the second nearest name. So this is something that David Loeb used. Yeah. So these are graphs on David Loeb. I will not explain that. So ransack is the one that we use to get rid of outliers. So ransack loop, as we remember from the previous lesson that we did today, randomly select a seed group of matches, compute the transformation from the seed group, find inliers to the transformation. If the number of inliers is sufficiently large, we compute the least squares estimate of the transformation on all the inliers. At the end, keep the transformation with the largest number of inliers. So we pictorially see this. Okay, now you can see between these two images, there is one image and this is the second image. You can see the matches. Two matches are wrong. The red matches are wrong, and the green matches are correct. So select one match, and we count the inliers. All these are inliers, and these are outliers. So like that, we can find the inliers. So if you select this, and only one inlier is there. These are outliers. So select the translation with the most number of inliers. So these 5 matches, green matches, we can select. That's the ransack loop. So you can find the translation there. Okay. So alternative robust lifelines, you can use so-called hub voting also. We will not look at that. So then with ransack, you can find transform accurately usually. But large scale alignment is also there. I will briefly describe that, but not in too much detail. So alignment with large databases is the thing. So those days before the deep learning came, when you give an image to Google to find similar images, these were the techniques that they used. So what if we need to align a test image with thousands and millions of images in a model database? Efficient putative match generation, approximately discrete similarity search, or inverted indices is required. So let's see what that means. So large scale visual search. Now you have a new image. Assume that you're putting some image of a flower or something. And okay, let's do that in Google and see that happened really. Okay. So let's open Google. So I want to go for image search. Search my images, so I can drag and put an image there. I'll do that. So I will put an image of a butterfly or something. I put it there. So then, yeah. You can see it was able to get things that look like that, right? So this is what we are talking about, retrieval of those. So visual matches, so many of them are there. Yeah, this is what we're talking about. But you can see Google has millions of images in its database, right? So our thing is how do we find them quickly. Because you cannot, if you give an image to Google, you cannot possibly think that Google will, for your search, match with all the billions of images it has seen. That is not going to happen. So Google has to have some faster mechanism of doing that. But now it's based on deep learning. But it used to be the techniques that we are describing now. Some before deep learning became popular. Okay, let's see how it's done. So these are the images features in the input image. These are the features in the input image. You can consider that these are shift features input image. Now Google, when it had time offline, for each of the images on the internet, it computed the features and stored them in a database. Stored in a database, but they stored in like this. They stored so-called inverted dictionary. For each of the features, let's take this feature. Let's consider that this as a special feature. For each of these features, what are the images on internet that have that? So IM1 has that. IM2 has that. Maybe IM7 has that. Like that. They did not store for image 1 what are all the descriptors. They for that descriptor, what are the images? Now you can see it's an inverted dictionary. So therefore you can query that dictionary with features. So that's the thing about quickly retrieving those images. So this is called inverted indexing. I hope you understand the value of inverted indexing. So then ranking and geometric verification happens after that. Geometric verification means the geometric arrangement of the features here must be there in the retrieved image also. How to do the indexing? Idea, find a visual code word to which descriptors are quantized. So descriptors are quantized. So here's a pictorial example of that. Now assume that we have this one, so-called visual code book. You have all the cars. From all the cars, you extract some kind of feature. These are not shift features, some kind of features you extract. But then you take all the wheel-like images and represented them using this wheel. You convert all half wheel-like images and represent them using these images. That's the code word 1. So this is a code book like representation of these features. So like that, you can make it more efficient. So so we will not go through the k-means clustering. So you can see this is one way of building the code book. So based on the code book, you can have this inverted dictionary for each of the code words. You list all the images. Now you can see extremely fast. You can retrieve those images for Google. So this is what I generally want to describe. I will show you. Hopefully, I'll try to show you one example also. I did not. I did not keep it ready. I will try to see whether I can get it. found it. So here is you have what is an example? So here you can see I'm superimposing the British flag on this building, right, on the four corners. So superimposing the flag there. So I will show that how I did that. First of all, I have to get this images open into new location now. Okay, so now I click 4 points. This one, this one, this one, and this one. You can see the flag gets imposed. Isn't that beautiful? Do it again. So here, this one, maybe this one, and this one. See, isn't that beautiful? So this is the kind of thing. So you have to compute the homography for that. So mouse clicking code in the previous one also I have. So I have the so-called Bantam image opened here and the British flag image opened here. Then after clicking the points, I'm trying to find the homography between them, and then I do the work perspective after that, and then add them. So something like this. That's the application. That's one application. It is a fun application, but I showed you an industry application also of this circuit board thing. Maybe I'll try to create an assignment on that and so that you can do it and see. So, any questions? We have a few more minutes left if you have any questions. You can see I have written ransack for complicated things. I have written ransack for this example. This one has both line and a circle. So doing ransack for the circle was not so easy. So, but I was able to get that working. Circle and
So for that, you mentioned some student who did a project on that tennis. Is it published as a paper or like as some?
he didn't publish. He did a final year project, and he's the first person to go to Google without a PhD. Nipuna Samarasekar, Island West. He did not publish that.
He didn't publish it, sir.
He didn't publish. He was so good. He didn't have to publish he's at Google. To go to Google, you need a PhD, but this one went there without. Any other questions? If not, we can conclude for now. I will create an assignment and give you. So please do that well, and you will feel very happy after you do that. You can see now slowly we are moving into applications. And next time I will talk about 3D reconstruction, how to make 3D pictures. These are only planar one still, machine. And after 3D one, we will move into neural networks. For that, you have to have PyTorch installed. So therefore, to install PyTorch, you have to type PyTorch installation. PyTorch installation. And you will go to PyTorch getting started. And there to install locally, you have to click what you have, like Windows stable, and if you have a GPU card, you have to go to command prompt and type NVIDIA SMI and see whether you have the Google CUDA installed. I have 12.6 here. So because I have CUDA 12.6, I have to click 12.6, and then it will give me how to get this installed, PyTorch installed. So you have to run this command to get the PyTorch installed. So I will put this in your WhatsApp group. So please have that installed so that we'll be able to do some little bit of coding with PyTorch next time. It's very important to have that. The reason is PyTorch has little bit of different constructs from NumPy that we need to understand. So we will go through a brief tutorial on PyTorch. If you have time, please go through a crash course on PyTorch also for us to start the neural network. Okay, then thank you very much everyone for joining. It has been 3 long hours. You stayed in the class. If you did, thank you very much. Have a pleasant evening, everyone.
Thank you, sir.
Thank you.